Hello everyone. In this video we're going to look at some applications of equations containing rational expressions. We'll start by simply solving some formulas for one of the variables that are utilized in the formula. Remember, the formula or a formula in general is just an equation. The difference is from a regular equation we're used to dealing with. Those equations usually have just one variable in them. Formulas usually have more than one variable, and in fact, they sometimes have the same variable in more than one casing. For example, there may be a lower case and the uppercase of the same letter, and they would stand for different things. So you have to be very careful when working with formulas to be aware of the case as well as the letter. So here we're trying to solve this formula from optics, where f is the focal length, u is the distance between the object and the lens, and v is the distance between the image and the lens. They're related together by this formula, and we want to solve this formula for u. So we're going to approach this very much like we approached the equations in our previous video when we were solving equations containing rational expressions, by basically finding the LCD and multiplying up on both sides. So here we notice that the LCD is very simple. It's just going to be FUV. So we go ahead and multiply that FUV on both sides of the equation. 1 over F equals 1 over U plus 1 over V. So don't forget that when we multiply it on the right side, because it has more than one term, we're going to distribute it. So, and we're multiplying it on the left side as well. So in the end, every term needs to be multiplied by the LCD to use the technique. So we get 1 times FUV, 1 times FUV, and then like so. So we just multiplied both sides of this equation by FUV, and of course on the right side we distributed. That's why we see it in two places. We actually are only multiplying it once on the right side, then we distribute. That's why you see it next to each term. So now we're going to go ahead and cross cancel as much as we can, and if we've done this correctly, the next step should give us a much simpler equation with no fractions in it. So you get UV equals FV plus FU. And now remember, we're solving for U, right? So we're going to go ahead and focus on getting the U terms next to each other. So we notice there's a U term here and one here, so we'll move this one to the left side. So we get UV minus FU equals FV. Now, we still have the problem of needing U by itself. So how are we going to get U by itself if it's appearing in these two spots? Well, remember, if it's appearing in these two terms, that means it's the GCF of those two terms as well. So we can factor it out. So we get U times V minus F equals FV. Now, all we have to do to get U is divide both sides by this V minus F. So that's what we'll do. And we notice that it cancels on this side, so we end up with U equals fv over v minus f. So one good sign to look for when you're solving for a given letter, make sure you don't see that letter on the right side anymore, because otherwise you haven't really solved for it, have you? So that's a good check always to make sure that something really hasn't gone wrong. So there you go. There's the letter U solved in terms of f and v. All right, make sure you can handle that. Try solving it for another letter. Maybe try solving it for v, for f. That'll be good practice. Okay, so here we have another problem. Now we're going to solve this formula for b, and the only thing that I really want you to pay attention here is that you only have one fraction line here, so that's just one fraction. And notice you also have only one fraction on the left side if you throw a 1, and you always want to catch those and never let those go by you, because that means we have a proportion situation going on here. So when we have a over b equals c over d, remember this implies we can cross multiply, so AD equals BC. Of course, why is that true? It's very easy. Just multiply both sides of that equation by BD. Watch what happens. B cancels B. D cancels D. So you get AD equals BC. The order of operation doesn't matter because it's multiplication. You can write CB or BC. So we usually just write AD equals BC. So this makes proportions very easy to work with. So you never want to miss one. So here we're just going to start by just cross multiplying. So we get, and remember that's capital U, right? So capital U times capital B plus VB. Remember, here's one in which we have both capital B and lowercase b, and we're solving for lowercase b. So equals, so here we're doing the A times D equals B times C, so VT. All right, the V is lowercase and the T is capital. All right, now remember, keep your eyes on the target. You're solving for lower b, right? So we're going to, since it's trapped inside this group, right, we're going to go ahead and distribute the u. So we get ub plus uvb equals vt, right? Keep your eyes on the target. We're solving for b, right? So there's only one term containing it. That makes it a little easier to work with. So we just want to isolate that one term first. So let's go ahead and get rid of the ub by subtracting it from both sides. So we get uvb equals u times capital B, right? Minus, let's write the vt first. It'll look nicer rather than writing the negative ub first. So we'll write this after the vt. That's nicer. So we just subtracted ub from both sides basically, right? So now all we have to do, we're almost there. To get lower b, we just need to get rid of this uv. Since uv is multiplied by b, how do you get rid of it? You divide it off. So we're going to go ahead and divide both sides by uv. And now, of course, that cancels, u cancels u, v cancels v. So you end up with lower b equals vt minus u times upper b divided by uv. Notice no lowercase b on this side. we should be in pretty good shape. And that should do it for that problem. So you want to get very comfortable with solving formulas for pretty much any letter in it. So make sure you can handle that before we proceed. All right, so in this problem, we have the ideal gas law from chemistry. And we're going to solve this for V2. So remember, you see the beauty of what's going on here? One fraction equals one fraction. A over B equals C over D. What is that? Well, in algebra, we call that a proportion, okay? So this implies AD equals BC. Now, if you go into a statistics class, they'll refer to something else as proportion. You don't want to get confused there. In algebra, when we say proportion, that means a statement of equality of two ratios, right? In statistics, they usually mean a part of a whole. So you'll be fine once you get there. You'll know the difference in context. All right, so here we do have a proportion scenario, so we're going to go ahead and cross multiply. It's the fastest way to get a solution when you have a proportion, so for any of the letters. So we want to solve for V2, so let me write this product first. That way it'll be on the left side, it'll look a little bit nicer. So we have P2 V2 T1. Those stands for pressure, volume, and temperature. Initial pressure, initial volume, initial temperature, final pressure, final volume, final temperature. So equals, so we wrote this cross product first. So on the other side, we'll write this cross product. That's what those two are called. They're called cross products. So we get P1, V1, T2. Remember what we're solving for, right? V2. So all we have to do now is get the V2 by itself. That means P2 needs to go and T1 needs to go. So we're going to multiply both sides by P2 T1. Notice P2 cancels P2, T1 cancels T1. So we're left with V2 equals P1 V1 T2 over P2 T1. The least amount of check you should do is to make sure that there is no V2 left in here, and it's not, so we should be good. All right, that's how we solve those. Here's a actual word problem related to proportions. In a certain country, 24 out of every 100 persons had been to Maui in a given year. Good for them. Fantastic place. If the population of that country at the time was 200 million, how many individuals had been to Maui? Okay, so this is a great example of a proportion problem. So we know that, so we just set it up like this. We say the denominator is going to be the total. On the top, we're going to have the part that associates to that total for the given scenario. So we know that out of 100, when the denominator is 100, the numerator is 24. So in other words, the 100 is the total number in the sample, and 24 is the number that went to Maui. So now we want to increase the sample size, right, to the population of the country. So we're going to have 200 million and we want to know how many would have gone to Maui. So like so. So the way you say it is, if out of 100, 24 went, then out of 200 million, how many went? So it's just a simple proportion. Or you say 24 is to 100 is like how many to 200 million, okay? So now we just have to solve this simple proportion. Again, we're going to start by cross multiplying. So we get 100x equals 24 times 200 million. So x equals 24 times 200 million over 100. So now we'll just get some help from a calculator. Okay, so we just need to type in 24 times, actually let me go ahead and put the entire numerator in some parentheses. So 24 times 200, and then 1, 2, 3, 4, 5, 6, 200 million, and then we're going to get out of that. So let me make sure. 2, 4, 6, 8. Okay, and then we're going to divide that by 100, and we get basically 48 million. All right, so if out of every 100, 24 had gone, then out of 200 million, most likely 48 million would have gone to Maui. All right, so now if you didn't want to write all these zeros, you could have just used 200, but then you would have put M, capital M, next to it to know you're dealing with millions. So you would go like that. You'd say 24 is to 100 equals x over 200 m. We can use capital M to realize it's million. So you want to keep that with you and not forget to carry it. So here we would get 100x equals 24 times 200 m. So then divide both sides by 100. Just keeps the numbers much smaller this way. Hundreds cancel out. On this side, 100 and 200 leave us 2. So we get x equals 24 times 2m. So we get 48m. And that's basically it. Just remember, m stands for a million. So if you really wanted to spell it out, at this point, replace the capital M, of course, with 6 zeros. And you get the exact same thing that we got over here. So this is something a lot of people prefer doing, just so that they don't have to keep writing all the zeros. I wanted you to see both options. All right, so here we have a boat in a river situation. Literally, that's what these kinds of problems are called. They're called boat in a river problems. And in fact, they don't just apply to a boat in a river. Anytime you have an object moving through some kind of a current, all right, which has a fixed speed, whether it's a boat in a river or it could be a plane going through a body of wind. So it depends on the situation. It doesn't always have to be boats and rivers, but anytime you have an object moving, in a certain medium of constant speed. All right, so here we have a boat in a certain river that can travel 12 miles with the current in the same time that it can travel 9 miles against the current. If the speed of the current is 3 miles per hour, find the speed of the boat in still water. All right, so here it's really useful to have a graphic to look at. So you have, well, you're gonna have to really forgive my drawing here. All right, I'm gonna do my best. Let's suppose that's a river, and let us suppose that's a boat. in that river. Let me use a different color. Now, let's assume that this river is actually flowing in this direction, and let's say the speed is c, and let's assume that the speedometer on this boat shows a speed of b, right? So notice that since this boat is going in the same direction as the river, we call this scenario that we have here downstream. I really wish these whiteboards would be less touchy. Downstream, okay? And if you think about it, when the boat's speedometer shows B, that just all that it's telling the viewer is that, hey, given the type of engine that I have, if I were in flat water with the kind of energy that I'm exerting, I would be traveling at this speed, right? But that doesn't mean that's how fast the actual vehicle is moving, because there's an external force here helping it out. So your overall speed, we call that the downstream speed. So rate downstream like that is actually going to be whatever the speedometer shows plus the amount that the current is helping it. So that's the downstream scenario. Then we have the upstream scenario. So in this case, you're in the same river, right? And now let's say it's in the evening, you went downstream to your work, now you're gonna go upstream back home. Now, of course, the river isn't gonna make a U-turn for you, is it? The river is always gonna go in that same direction. And your speedometer is once again showing B, but remember, this time, you're actually not going quite B, are you? The rate upstream is going to be whatever your speedometer shows minus whatever it may be slowing you down. In this case, the current is fighting you. You're fighting against the current because you're going against the stream. That's called upstream. So your speed, your rate, which is the fancy word we use for speed in mathematics, going upstream is going to be whatever your speedometer shows minus the speed of the current, which is fighting against you to slow you down. So now we're going to set up a nice table. We know that rate times time equals distance, right? So there's always an equation that is going to help us find our proper table and the proper equation. So if we set up a table like this, we can dedicate one row to downstream motion and one row to upstream motion. So we're going to be dealing with rate. It's good to put the units so that you don't have to put it in every box, to put it in the header of the table. Time here is going to be in hours, and distance here is going to be in miles. All right, now if you want to write it more mathematically, you could put mi per hr. All right, or just h. Sometimes people just use h. All right, so Let's see what we have now. We know the distances, don't we? We know that a boat in a certain river can go 12 miles with the current. That's downstream. So we know this is 12. In the same time that it can travel 9 miles against the current. That's upstream. Now, a really important magic word, in the same time. We're going to get back to that in a second. Now, we know the speed of the current is 3, right? So that means instead of rate downstream writing B plus C, we can actually put down what C is. We know what it is. It's 3. The speed of the current is 3. So we can put B plus 3, right? And instead of for the upstream writing B minus C, we can just write B minus 3, right? Because we know what C is. Now, just looking at this scenario, we know that the time going downstream is going to be, remember, rate times time equals distance, right? So that means time equals distance divided by rate, right? If we just solve that simple formula for t. So we know that this time here for the downstream movement is going to be 12 over the rate, which is b plus 3. And the time for this upstream movement is going to be 9 over b minus 3. Now this all important phrase comes in the same time. So what does that tell you? That tells you those two times are equal because the time downstream is the same as the time upstream. Of course, notice it's the same time, but because in one case you're going faster, you cover more distance. In this case, you're going slower, so during the same time, you're going to cover less distance. So that makes sense. So now we're just going to take 12 over b plus 3, and we're going to set it equal to 9 over b minus 3. Now, that should be very familiar to you at this point. You can see that's a proportion. We can go ahead and cross multiply. So we get 9 times b plus 3 equals 12 times b minus 3. So 9b plus 27 equals 12b minus 36. Since the larger b term is on this side, I'll go ahead and respectfully move the b terms to that side. So I get 12b minus 9b, and I'll keep the 27 on this side and bring the negative 36 over to get plus 36. So now when we add those, let's see, we have 50 and 13, so that's 63 equals 3b. So we get b equals 63 divided by 3, which is 21. So this is a word problem, so we're going to answer it properly. We're going to say the speed of the boat in still water is 21. Now we're speaking regular English, so we're just going to use the MPH symbol, 21 miles per hour. And there we have solved the rate problem. This kind of a problem falls into a category of problems called rate problems. We deal with things very generally in mathematics. So we have a lot of different categories that could fit in here. You could have, anytime you have something being done at a certain fixed speed, it qualifies as a rate problem situation. So there are different applications that you may see using this kind of a scenario. And of course, like if you're stuffing envelopes at a certain fixed speed, you would get rate times time equals the number of envelopes that you've stuffed, etc. So depends on the situation. Depending on the situation, it's not always distance that you're covering. It depends on what the rate is describing you doing at a fixed speed. Here's another kind of rate problem called a work problem. So here, Al can mow their lawn in 3 hours. Mary wastes less time chatting to the neighbors than Al, so she can mow the lawn in 2 hours. So how long would it take them to mow the lawn if they start together and work until the whole lawn is finished? Okay, again, we call this kind of a problem a work problem. So there's a real nice simple way of setting these up, right? Remember, for each one, this is a rate problem as well. We have the rate times the time for that person equals the portion of the job that they get done, right? So for example, we can say rate for Al times time for Al equals whatever portion of the job he gets done. So let's say we want to see how long Al takes to do the whole job, right? So we know that Al does the whole job in 3 hours, right? So if we put 1 for the entire job, that gives us the rate for Al. The rate for Al is 1/3, okay? That means 1 job per 3 hours, right? So what does that mean? That means Al does 1/3 of a job per hour. That's what's considered to be Al's rate. Now we know we can set up the same thing for Mary. So we say rate Mary times time Mary equals jobs. Now we know that Mary can do the whole job in 2 hours, right? So if we set that equal to 1, we can find out what Mary's rate is. Notice it's 1/2. That means 1/2 of a job per hour. So in 1 hour, Mary does half of the entire job, right? So now we can go and make an equation that involves both of them working together. So we just go rate Al times Al. That's how much of the work Al will do. Plus, remember they're working together. So plus rate Mary times Mary, time Mary equals, remember we want them to finish 1 job, right? So instead of J, we're just going to put 1. So now, what is the rate? Do we know how long it takes if they're working together? No, that's what we're trying to find, right? But we know it's the same amount of time because they're going to start together and finish together. So we can just say TA equals TM, and we can just use T for them, right? Because they're both going to be working during the same period of time. And each one is going to be doing it, of course, at their own speeds. So Mary is just going to be working seriously. Al is going to be goofing off with neighbors a bit, but just at their own speed, right? So we know rate for Al is 1/3, and we know the rate for Mary is 1/2. And they're both working for the same period of time, so we'll use T for both times equals 1. See how beautiful and simple that is? Now all you have to do is solve that simple equation. So we're going to go ahead and find the LCD, which is 6, and we're going to multiply that on both sides. So we get 6 times 1/3 T plus 6 times, remember we have to distribute on the left side, so each of those terms is going to get hit by 6. So now we simplify. So 3 goes into 6 twice, 2 goes into 6 3 times. So now we have 2t plus 3t equals 6. So we get 5t equals 6. So t equals 6/5. And remember, of course, the rate for time is going to be hours, right? So what does that mean? That means they can do the whole lawn together if they start together and finish together, and each of them just goes at their own individual speed, right? So of course, if we don't want to sound like we're too distant from society, we don't want to say 6/5 of an hour or anything like that. So we're going to go ahead and make that sound a little bit more everyday conversational. So that means 1/5 of an hour. Of course, if you just divide 6 by 5, right, you get 151. And if you want to sound even more conversational than that, you can just say that's 1 hour plus 1/5. Now you can convert the hour into minutes on the 1/5. So you have the hour up here, so you multiply by a unit factor. You want 1 hour down here, and you know that there's 60 minutes in 1 hour. Now, why is that called the unit factor? Because the top and the bottom represent the same quantity. So now you see the hour cancels hour. 5 goes into 60 12 times. So now we can say, we can answer in a very normal conversational English that they can finish the job in 1 hour 12 minutes. That is, if they start together and finish together and each works just at their own individual speed. So that's what we consider to be an example of a work problem, where different entities are working on the same project, but each doing it at their own individual speed. Now, there are different scenarios that they may throw at you. Like, for example, they may say, what if one of them starts an hour earlier, right? So you're still going to be able to use t here, but then you'll use maybe the other one will be working for an hour less, right? So you'd have t minus 1 there. Or you could use, depending on how you set it up, maybe you call one of them t and the other one t plus 1. So anyway, just be ready to adjust for some variations, but the basic strategy is going to be this: to set this main equation up where each one is going to contribute to the one job. All right, so make sure you can handle that setup before we proceed. That should actually be sufficient for today, so I think we'll call it a wrap at this point on this video. And make sure you practice these. They get a little bit of getting used to, like all word problem situations, but once you do a few examples, they become really simple. That's the magic of mathematics, right? It always looks impossible at first, then after a few you're like, wow, I can't believe that I used to think that was hard, right? So it just perseverance and careful practice, of course. So stay safe until our next video.